Chapter 4. Texture. The last section equated the basic recursive cycle of motion to the ideal field model and briefly mentioned a texture on the surface of energy which has become bound in a self-interacting feedback loop, matter. This texture is the pattern of the motion itself and can easily be seen in a glass of water. When the glass is vibrated, the motion, vibration, causes a texture change on the water's surface. To understand the mechanics of motion in greater detail, this texture will now be examined. As was explained in the previous section, motion through a medium causes that medium to compress together and thus gain in energy density at the point of contact in the act of transferring the motion energy. This happens in a specific pattern, ideally as the ideal field model, but more often in inferior patterns, which give rise to the specific characteristics of matter. Occasionally, portions of the medium get bound into this higher energy state and become a recursive reflection on a lesser magnitude of the movement pattern which has spawned them, thus becoming a particle. Therefore, any particle is quote-unquote denser than the medium that compressed to create it, and possesses a unique pattern of vibration. The ideal field model is thus an energy density gradient, with the center as the most dense to the exterior as the most rarefied. The cycle of energy density propagation, follow the red arrows on image 22, begins at the center of the model as one compact force of the initial prime movement. It then spreads out as the interior vortex in the direction of the axis vector rarefying towards the surface. Then it cascades in a spiral on the exterior surface to the opposite pole and recompacts on its return to the center to fill the potential void. Remember that the nines on the model, represented as small blue circles on the violet band, are also minor vortices. They too follow the same density gradient, with the center of the vortex the least dense. Like the tube of air that runs through the center of a water vortex. This center column of the vortex, though less dense, also follows the gradient, getting denser towards the center of the model. The exact nature of the final form created by this cycle is dependent upon the characteristics of the specific wave traversing the cycle. Image 21 shows the energy density recursion of the model. In reality, there would be infinite levels of recursion so close together that they would be nearly indistinguishable. However, to exaggerate this, only 3 levels are shown in the model for clarity: a blue sphere inside a yellow sphere inside a violet sphere. The blue sphere being the most dense and the violet sphere being the least dense. Their collective axis vortices get smaller from the violet to the blue, which causes the smooth interior vortex, as seen in image 22, the same vortex seen when draining water. Image 23 is a hypothetical energy density cross-section of the solid ideal field. Density is denoted as the darkest being the least dense. The gradients are exaggerated for clarity. Normally, boundaries would flow smoothly one into another. It is this network of densities that creates an architecture in a system. Image 24 highlights in red this architecture surrounding the vortices, which is the result of the boundaries of their flow, the highest densities being where the edges of the vortices meet. Image 25 shows how this gradient would basically appear on the exterior surface of a system. Image 26 roughly details the flow of energy of the minor vortices while still maintaining the spiral path of the major pole vortices. These spirals must be imagined in 3 dimensions, each descending in towards the center of the system and then out again. Note, do not allow the limitations of these examples to restrict your visualization. The possible number and size of vortices could have infinite combinations. The examples shown here are simply for clarity. It is also important to understand that the architecture and the vortices are not separate. They are simply easier ways to visualize a continuous energy density gradient. For example, image 27 shows that the Earth and its corresponding magnetic field are at different magnitudes of energy density from the center outwards. Even the magnetic field rarefies further from the center. The Earth and its field are too often looked at as separate, when they are actually one system. However, they could be analyzed independently due to the recursion of the ideal model, image 21. To further illustrate, the electron cloud and nucleus of an atom are likewise simply levels of magnitude of an energy density on a continuous gradient. Likewise, the nucleus of the atom is also a continuous energy density gradient with merely the potential to be split into those units called protons and neutrons. Lastly, the visible part of the sun is only a tiny part of the titanic quote-unquote solar system, whose most rarefied levels extend beyond Pluto. The density of a system decreases from its center to the perimeter, and all of its composing units have a proper level of density within it. Any unit within the system will be at a distance from the center directly dependent upon its own energy density. All units are forced towards their proper layer of density by the action of more energy-dense units. The exterior texture of a system is the result of its energy density fluctuation pattern, which is a spiral wave cycling over itself along a spiral path, forming a net disturbance on the surface from its constructive and destructive interference with itself. Understand that with infinite recursive levels of magnitude, the surface is defined by the level of magnitude one is examining at a specific distance from the center of the system. This disturbance can be violent, uniform, irregular, etc., all depending upon the nature of the medium and the characteristics of the cycling wave. The minor vortices in a system are the valleys of a net waveform whose cycle is the complete circuit between the two major pole vortices. Their flux, the dynamic wave pattern, spouts like a spiral fountain out of the positive vortices and into the negative ones, image 28A and B. In a disturbed surface, the more dense energies closer to the center occasionally are energized by a flux flowing to higher magnitudes and thus gain enough energy to temporarily rise up from their normal rest level of density into a more rarefied level. The field lines they follow may not be the spiral of the ideal field due to the medium's limitations in acting as more ideal energy, coupled with its energy requirements to do so. The more ideal pure energy the medium being moved is, the closer it will obey the ideal field model. This is illustrated with a low amplitude vibration in a glass of water. First, the surface texture will hardly change, but raise the amplitude to a significant level, and the water may actually splash out of the glass from the violent surface fluctuations. This can be further illustrated at the base of any water spout, image 29. The air vortex represents the more rarefied vortex flux, and the toroidal mound at the base of the spout is the denser medium, in this case water, being temporarily raised into a more rarefied order of density, while attempting to mimic the vortex dynamics on a higher level of magnitude, yet with limited energy. One can observe the same spouting toroidal mounds as solar flares on the surface of the sun, image 28C. A quote-unquote order of magnitude of a system is simply a smooth sphere at any distance away from the center of the system. The larger the distance, the larger the order of magnitude. Image 30 shows this in violet and red, red being the highest order of magnitude of the system. In contrast, green shows a single level of energy density by highlighting one specific shade. Notice how an order of magnitude, violet, will extend over multiple energy densities, and one energy density, green, will traverse multiple orders of magnitude. The one has a fine texture of numerous densities, the other a rough texture of one density. Imagine the violet ring as an electron cloud. The denser areas would be the electrons. It is these textures which govern the interactions of systems, because the difference in energy density govern energy flow in the universe. Basically, less dense energy always flows around more dense energy unless it is forced into a point of obstruction, explained later. Less dense energy can be made into more dense energy by imparting motion, Zp energy, to it with pressure. Motion is transferred when two systems touch in proportion to their pressure. A simple way to visualize this interaction of systems is by gears, because this texture is toothed in a sense. This makes it easier to visualize and map the complex interactions of frequencies and amplitudes stirring around inside a system or between two systems. These teeth are a general map of the system's potential to engage and affect another system in proximity, from solar systems to atoms, based off of its cycling waveforms. Frequency and amplitude are the number of the gear teeth and size of those teeth, respectively. Image 31, in red, 1 would be amplitude and 2 would be wavelength. The adjacent image represents a compound waveform. These gears represent the pattern of a system's waveform. The peaks of the wave have precise domains, which can be thought of as teeth. The constant internal fluctuation of a system causes the peaks to cycle across the surface, resembling spin. When energy is added to the system, this spin increases. These teeth represent the system's attributes when engaging another system, and so too do the anti-teeth, which would be the valleys of a wave. For example, the above gear of R4 may interact with R3 temporarily in cycles, or with a smaller quote-unquote gear temporarily engaging between the longer teeth, only to then get violently struck away by the longer tooth when it cycles through. However, if the placement of the smaller gear was such that it only interacted with the outermost order of magnitude, a continuous cycle could be maintained. These examples are all very simple, and when compounded waveforms are introduced, the texture of the gear and its cycle could be very intricate, as well as its interactions with other systems. This texture of any order of magnitude of a system is composed of only the waves of a given energy density that emanate beyond the chosen distance from the center. However, the ideal gears are three-dimensional spheres, not two-dimensional disks. If one takes the commonly visualized two-dimensional wave in image 32 and realizes that it is actually a three-dimensional spiral, and then closes it into a circle, one gets the early ideas of what a string might look like. Image 33. However, this is far from the ideal model, because the path of the spiral wave is still on a 2D plane. When the path is made into a three-dimensional vortex and cycled through itself, the ideal field is created. To visualize these teeth in 3 dimensions, observe the spikes of the ferrofluid, image 34, as gear teeth, but imagine them not as iron, but as a charged elastomer, pliable yet firm. In the presence of other gears, such pliability and charge allows them to line up and mesh perfectly. Another example of the texture of the ideal field is, oddly enough, a pineapple, image 36. Imagine the teeth of the pineapple as being different sizes in certain patterns, and possibly even fluctuating due to internal constructive and destructive interference. Also, imagine the peaks and valleys, each as a miniature textured vortex, as the nines on the ideal model. Just as the vortex draws in energy from one side and spews it out the other along its axis, the pineapple sucks up water from its base and spews out a crop of green leaves from the top. Note, image 35 is the quintic string, which is physics' present attempt at visualizing the string. Notice how it is evolving into a pineapple-like texture from the earlier 2D toroidal form.